Hi, welcome back to our third segment. In this hour, we're taking a look at organic molecules, and we are doing some past paper questions from the DBE 2014 paper. One of the things that we looked at is why we wash our hands and use hand sanitizer, and that's down to the properties of the organic molecules. And I've chosen this particular question because it goes right from microscopic up to macroscopic, and hopefully you can kind of get an insight into what the examiners are trying to do. I've marked many matric papers before. We are not trying to trick you, I promise. But they are very, very specific in what they're looking for. Hopefully I can give you a few clues as to why they give certain questions, certain marks, and this is something I don't often see done in lessons. Okay, so now when you're starting to take a look at papers like these, you always start out with the microscopic. Microscopic, like the individual bonds between atoms or the molecular shapes, and there's not a lot you can do if you don't know what's going on with the molecules themselves. It's really important that you know the basics, like how saturated versus unsaturated, polar versus non-polar. You need to know these basics. Okay, so if you don't, calm down, don't panic. We've got a lot of time and we can work through this together. So first question, 3.1. It says, give a reason why alkanes are saturated hydrocarbons. Okay, so now again, starting with the microscopic, when we start to deal with an alkane, like let's say ethene. Now ethene, weirdly enough, is quite common. We find that it seeps out of the ground in nature. It's one of the natural byproducts that comes off decomposition deep inside the ground. Why are they called saturated? Now the word saturated means full. When something is saturated, it means completely full. Now, what is completely full? Well, in organic chemistry, most of the time when you start dealing with anything, you are talking about carbon. So it says that the carbons are full. So these two carbons are full. Now, what are they full of? They're full of hydrogens. Now, the answer that they are looking for that one mark is that the carbon is single bonded with another carbon, leaving all of the other bonds free to bond with other things like hydrogen. Okay, so now when we start taking a look at saturated hydrocarbons, we are looking for that single bonded carbon-carbon. That is why alkanes are regarded as saturated hydrocarbons. Now here's where the real business starts. Write down the structural formula of the functional group of alcohols. Now, I marked a question like this. Now this is very misleading. They want the structural formula. That means that they would like to see how atoms are bonded to each other. You need to draw in the bonds. The functional group of alcohols. Okay, the name of that is a hydroxyl, but that is not the answer to this question. Okay, so now the name of it is a hydroxyl, but there is a lot more to it than this. We need to draw the structural formula of this. Okay, so now let me just get an empty page and let's talk about this. Okay, so now when we draw out a hydroxyl, that is the functional group. Now, that is the name of the functional group, and I know a lot of people this year answered this, but it didn't answer the question. They're looking for the structural formula of this. The structural formula of this is OH. Now, you can draw it as dash OH, but that's not really showing all the bonds inside. Just to be safe, dash O dash H. Now, that is the structural formula. You're actually showing all the bonds inside there. Okay, so that is the structural formula. Okay, now when you start to take a look at the functional group, something really important is that we need to take a look at the family of molecules. But the correct term for this family is a homologous series. So if they're looking for the homologous, oh, excuse me, writing very, very badly there. Okay, a homologous series is a family of molecules which all share the same functional group, and that is alcohols. Now, the reason that I chose this question was because the alcohols were the really good sanitizers. Which alcohol were they talking about in this particular one? They were talking about butane 1-ol. Now, they wanted a tertiary alcohol, that's quite complicated, which is a structural isomer of butane 1-ol. Okay, now I'm just going to leave that up for a second in case anyone wants to digest that sentence. A tertiary alcohol that is a structural isomer of butane 1-ol. Sure, that's quite a mouthful. Okay, so first of all, before you draw isomers of things, draw out the original molecule, please. Butane 1-ol. Okay, so now how do we draw this out? First we draw the bute bit. So bute is 1, 2, 3, 4 carbons. An, single bonded. So it's from butane. Then it tells me that on the first carbon there is an ol. That means that there is an OH on that first carbon. Okay, now the first carbon can be from the left or from the right. Doesn't really matter, but it's got to be on the end. So that is butane 1-ol. Okay, now if I want to draw a structural isomer, this means that I've got to rearrange these same atoms to keep it an isomer. But here's the thing, it needs to have a completely different arrangement of the bonds inside. But a structural isomer, a really tricky thing, because anytime you rearrange the bonds, you can change the molecule's functional group, which makes it a functional isomer, which is also a type of structural isomer. All they're looking for you to do is to rearrange it, but they would like to have what is known as a tertiary alcohol. This is a primary alcohol, and I'll tell you why. Because look at where the hydroxyl is. The hydroxyl, or the functional group there, is on a carbon joined to only one other carbon. So that is a primary carbon. Now, if I draw butane 2-ol, for instance, if I put it onto this carbon, that would make it into a secondary alcohol. But now a tertiary alcohol, this is the really, really challenging thing. Okay, hopefully your battery is not running as low as mine. A tertiary alcohol is one where you've got a carbon sticking to 3 other carbons around it. Okay, now let's look at something which might allow me to do that. Let's kind of see what that might look like. What is tertiary? Okay, tertiary is when I've got one carbon stuck to 3 other carbons around it. Kind of weird, right? Now that carbon is a tertiary carbon. Now, if I complete this and I fill in all the hydrogens, keeping all the hydrogens saturating the carbons, because you won't change the saturation of a molecule just by rearranging it. I hope you can still see that on your screens. And I put that OH, let's put it there in a different color just to make a point. I can see that this OH is attached to a tertiary carbon over there. See, 1, 2, 3 carbons around it. That means that this is a tertiary alcohol. Now, I always make students rename molecules when they've made an isomer, just to prove that it really is an isomer. Because if you have made an isomer, it will make a different molecule. A different molecule is going to have a different name. I mean, that's the rules in organic chemistry. IUPAC rules say that if you've got a different structure, it's got to show inside the name. So let's take a look at what this isomer looks like with a different name. Okay, now here's the tricky part in finding the longest carbon chain. It could be that way. It could be around the corner. Remember that you can count around corners. It doesn't actually matter. Here's a really weird thing. It's the beauty of organic chemistry, is that no matter which way you count it, you can do this. Okay, so if I say that that is the longest possible continuous carbon chain, so that is 1, 2, 3. That means that this is no longer butanol. So that is prop. They are still single bonded. So it is propan. Okay, now there's a couple of things on the side chains, and this is really important. So I've got a side chain, which is a single carbon side chain, so that is methyl. And I've also got a hydroxyl, which is an ol. Where they go on the molecule is quite important. So side chains go on the front. Things which replace hydrogens generally go on the front, like metals. If you find, chloro, bromo, iodo, those all go on the front. And where is it? It's living on the second carbon. So it is 2-methyl propan, and take a look also on the second carbon, propan 2-ol. Now that's a real mouthful for something which is an isomer of butane 1-ol. In fact, there is a acceptable term which is given to this really weird arrangement of butanol. This is actually called T-butyl, but this is something that you probably won't learn about in school chemistry. T-butyl alcohol is the other name for this particular chemical, and that is accepted by IUPAC, but the most accepted one that you will find in your exams is this one, 2-methyl propan 2-ol. Super difficult. So the question is, if you were to take a look at these two molecules, how would their intermolecular forces differ? Well, I hope that you saw that you've got this OH, which allows you to hydrogen bonding, and let's actually label that. This slide is getting very busy. Okay, so that can do hydrogen bonding. These two molecules, because they are isomers, have got exactly the same molecular mass. That means that it's not going to be down to a mass, but one of the things that you'll find is that hydrogen bonding on a secondary carbon is less effective, on a tertiary carbon even less effective. So what you'll find is that there will actually be a boiling point difference between these two. Even though butane 1-ol and 2-methyl propan 2-ol are isomers with exactly the same mass, able to do exactly the same intermolecular force, you will find that tert-butanol or tert-butyl alcohol will have a slightly different boiling point, and in fact a slightly lower boiling point than butane 1-ol. And the reason is that hydrogen bonding is not that effective on a tertiary carbon. Okay, let's just go back to the question, make sure that we've answered all of the points, make sure that we've got all of our answers correct. So what we're going to do is just make sure that we've got full coverage of those. Let me just make sure that I've got, yeah, there we go. Right, so did we get the functional group? Yes, we did. Did we take care of the second bit? A tertiary alcohol that is a structural isomer of butane 1-ol. Now, there's a difference between just being a structural isomer and being a functional isomer. Now, functional isomer we'll talk about a little bit later on in the show if we get a little bit of time, but it's really, really important that you know what a structural isomer is. Guys, I'd like you to practice this to absolute death because it comes up in every single exam question, is make a functional isomer of this thing and say, okay, well, what is the difference between them? Name them. Because I see a lot of people rearranging their molecules and they don't actually come up with a different molecule. They actually come up with the same molecule just bent in the middle. Let me actually show you what I mean. Somebody in an exam question I was answering, or sorry, at least marking, I wasn't answering it. You guys were writing the exams, doing the difficult bit. They said, okay, well, here is, for instance, pentanol. So pentanol's got this OH over there, the hydroxyl's on the first carbon, and they came up with an isomer of this, where they changed where the OH was, and let me just give you an example of where they put it. So they took the OH off here and they put it on the other side and they said, well, I've moved it. Have I actually made an isomer? No, I haven't. They said I took pentan 1-ol and changed it into pentan 5-ol. Not possible. That actually made the same molecule again. This molecule can flip around, and it does. So please be very careful. Remember, when you are making isomers, rename it. Make sure that you come up with a different name. Wash hands. Come back after the break.